Hello and welcome back again to this lecture course on principles of polymer synthesis, and in keeping with the theme of this week's concept, we are continuing to talk about principles of radical chain polymerization. And in the last class, the point at which we left is we had actually derived a relationship of degree of polymerization, number average degree of polymerization with the different chain transfer material concentrations and their corresponding constants. So, this was the equation where we stopped in the last class. So, 1 divided by x n, and that is related to R t and R p both, they and you have all these extra terms. So, C m is the monomer chain transfer constant, C s is the chain transfer constant to say solvent or the chain transfer constant to an external compound that you have added. So, in that case typically there is a name for that kind of compound, that is chain transfer agent. So, because you know all these things will modify your molecular weight, because they are modifying your x n bar. So, these chain transfer reactions are stopping growing chains. So, that correspondingly they are actually limiting your molecular weight. So, if there were less chain transfer reactions, the chains will grow more, molecular weight will become higher. If there is say more effect of the chain transfer, so your molecular weight can be limited. And you can see that there is also an opportunity. So, this may be a detrimental thing for your system when you want to obtain a high molecular weight and all these things, say you have a chain transfer to a solvent. In that case it is limiting your molecular weight, or the initiator that you are using, there is a chain transfer to that initiator, that is limiting your x n bar. So, these things are detrimental to your objective. However, you can look at it another way, that since this particular expression gives you a quantitative estimation of how the different species or different contributions of chain transfer to different species, say to the monomer, to the solvent or to the initiator, that affects this x n bar, this gives you an opportunity to control the x n bar also. If you want to get say a specific x n bar, then correspondingly you can analyze the effects of all these things, say chain transfer to monomer, chain transfer to solvent. Okay. So, if you want to control the x n bar, for example, so let us say for the moment instead of solvent you are putting it as, let us say the S stands for an external agent, that means a chain transfer agent. You can actually add a chain transfer agent and that will limit your molecular weight to the extent that you want depending on these equations. We will have a more detailed discussion of this today. So, this particular expression that you have here, this is called Mayo equation, which is very important to analyze for radical polymerizations. Now, in order to understand the importance of this expression more, you have to have experimentally measurable quantities that are coming here all the time, because you have to measure those quantities in order to get something out of this equation. You need to know what is the value of Cm, the monomer that you are using for polymerization, what is the extent of chain transfer to that monomer from a growing radical species in that particular system that is actually limiting your molecular weight, that also you need to know. So, those things, so you have to express these in measurable quantities. Of course, R t and R p you can measure, we will not go into the details of how you can measure some of these things, but we will actually split it into different parameters and give you some idea about how some of them can be found out. So, this particular ratio, so I will work here in the background, say R p by R t is nothing but R p by R I, because rate of initiation is equals to the rate of termination, steady state assumption. Now, this ratio was nothing but K p into m dot divided by K t into m dot square. So, m dot will be at the bottom and this will be K p into m divided by K t, and m dot is nothing but R p divided by m from this particular expression, R p divided by m into K p. So, from here m dot, from here m dot is nothing but R p divided by K p into m. So, you are replacing this m dot by that. So, it will become K p square into m square. So, you just replace that term here. So, what you will have then is nothing but K t into R p divided by 2 Kp square m square, Rp divided by Rt is nothing but this. So, you are putting that value here, plus Cm plus Cs into S by m. It could be solvent or it could be a chain transfer agent, an agent that is added from outside to control the molecular weight, and plus Ci into I. Now, the expression of I, again let us work it out over here in the background. If you recall this particular expression, Kp into m into f Kd I divided by Kt to the power half, you know, it might appear to you that there is a lot of calculation involved here, but many of these things will give you important conclusions about your experiments that will help you to engineer the polymerization reaction, that you have to understand. So, you have to look at this analysis in those terms, not like some boring mathematics. So, from here you can have an expression of I in terms of all these things. I am just writing down that expression of I here. From here, if you put the I in terms of all the other things. So, it will be Ci to Kt into Rp square divided by Kp square into f to Kd m cube. So, this is the expression that you have. Now, the next stage for us is to try and find out what are the values of this. Otherwise, this equation has no meaning. You need to know the rate the chain transfer constant for different species, for monomers, for solvent, or for a added agent which is your chain transfer agent, for the initiator the Ci value. How do you know all these things? So, let us go into that particular part now. So, the determination of, so let us say you are trying to determine the values of Cm and Ci. I mean, as far as the Cs is concerned, we will come to it after. For the moment, let us assume there is no chain transfer to the solvent, plus you have not added any chain transfer agent to the system. So, this term will become 0. So, you are left with only these 1, 2 and these 3, the 3 terms on the right side to deal with. So, you have then this expression 1 divided by xn bar equal to Kt Rp divided by 2 Kp square m square plus Cm plus Ci into Kt Rp square divided by Kp square f Kd m cube. Okay. Look at this term Kp square by Kt, this is a very important term that is making its appearance in many places. Even if you are looking at this expression of Rp, you have this term Kp by Kt to the power half. If you take a square, it will be Kp square by Kt. So, those terms are here. So, if you can measure the value of Rp by some experimental means, independent experimental means, then this Kp square by Kt, this term is known, because you know the concentration of the monomer, you can find out the efficiency of the initiator, and correspondingly the Kd value can also be known, and I is already known. How to determine the Kd values, probably we will not discuss that much, but there are ways to determine. So, this particular expression, if you look at, this expression is quadratic in Rp. So, what you do is you plot this 1 divided by xn versus Rp, you plot that. Now, if you are plotting 1 divided by xn versus Rp, what you will get? So, in the initial stages of the plot, if you are plotting 1 divided by xn versus Rp, you will get a linear plot initially in the initial stages where the Rp is low, because if the Rp is low, then the contribution of this term becomes low. So, it will be then linear in Rp, and later on it will deviate from linearity as Rp becomes higher. Now, if you compare this expression is nothing but concentration of I divided by m, actually it was nothing but this, you have replaced the I with all these expressions and you have got this. So, one of the ways to look at it is that So, when you are constructing this experiment, what you are doing? You are doing a series of experiments with different rates of polymerization. One thing you should remember, that determination of all these things are done at low conversion of polymerization. When the polymerization reaction has proceeded to a low conversion, not at a very high conversion, when it has proceeded to a low conversion to start with, at a very small conversion, what you do is that you measure all these things. So, at that particular conversion you can actually change your rates of polymerization. How you can change your rate of polymerization? By increasing the concentration of the initiator, you can increase the rate of polymerization. Look at that particular expression here again, all these expressions are related. So, if you look at that particular expression here, your Rp is related to I to the power half. So, you can increase the Rp by changing the concentration of I. So, you get all these different points at a particular conversion, say. Typically it is a low conversion, because if you go to high conversions, then what will happen is that your initiator concentration will drop, your monomer concentration will drop. In fact, your initiator efficiency can also change. So, typically many of these experiments are done at low conversions. So, these are low conversion data. Now, so this 1 divided by x n bar as a function of Rp, if you are plotting at a high value of Rp or at a high value of I, this term becomes important, this term is nothing but this term, this becomes important, and then it deviates from linearity. So, if you look at this particular plot, so initial portion is linear. Now, so it will be like this. If you look at this part, it is nothing but y equals to mx plus c. So, you are plotting, so this is x, so m is nothing but this, which is your slope, y equals to mx plus c, and this is your constant. So, mx plus c. So, what you can find is that from the slope you can find kt divided by 2, it is kp square into m square. So, if you know the value of m monomer concentration, that you know, so you can actually find this value of kt by kp square, which is a very important term that you can find from the slope, and from the intercept you can find the value of Cm monomer chain transfer constant, because this becomes a linear equation. So, from the intercept you can find this monomer chain transfer constant. Okay. Now, what about Ci? So, if you are trying to find the value of Ci, you can rearrange this particular plot. But before we go into that, let us show you an experimental result that directly will come into the slide here. So, let us show you in the PowerPoint slide one experimental result. So, you can see that on the y axis you have 1 divided by x n bar into 10 to the power 4, and on the x axis you have your rates of polymerization, rate of polymerization. Now, the figure caption is like dependence of the degree of polymerization of styrene on the polymerization rate. So, this is a polymerization of styrene, and the different graphs that you have, they are for different initiators. Okay. Say for example, the open circle, the graph is for tert butyl hydroperoxide, and then if you have the closed circle, if you are looking at the closed circle or the filled circle, that is your benzoyl peroxide. Now, one thing you should keep in mind here is that some of the graphs are going to a large amount of nonlinearity at high Rp. Now, if your initiator, if your chain transfer to the initiator is negligible, suppose the chain transfer to the initiator is negligible, then that last term, which is your chain transfer constant into initiator concentration divided by m, that will be very low, because your Ci is very low. So, if that term is very low, then your graph will remain linear throughout. So, in the exam problem, suppose you are asked, you are given all these different graphs, because these different graphs are, all of them are for styrene polymerization, but they are generated with different kinds of different initiators. So, if for some initiator it is perfectly linear graph even at very high Rp, then that tells you that the chain transfer to that initiator is negligible, because that term does not come into the picture. So, it is a linear correlation of 1 divided by x n bar with Rp all throughout. The quadratic dependence only comes into the picture at high Rp values when your I, that Ci value is high. If your rate constant, sorry, if your chain transfer constant for the initiator is already low, that term will be negligible. So, that graph will be linear. If that graph deviates from linearity, if it deviates from linearity more for one initiator compared to another initiator, then for the initiator for which it deviates more, the chain transfer to that initiator is appreciable, that you have to keep in mind. So, these are some of the clues that you can get from this kind of graphs. I hope that you find that this is useful information. So, now let us go back to what we were doing. This Ci value we are trying to find out now. So, whatever graph we have shown is for the Cm value, the value of Cm, the chain transfer constant for the monomer. Now, what about the value of Ci, the chain transfer constant for the initiator? So, you have this particular expression, you can rearrange this expression like this. So, 1 divided by xn bar, 1 divided by xn bar minus Cm into 1 by Rp. So, you are actually dividing by Rp throughout, and you are taking this term on, you are taking this term on this side, and this equal to Kt divided by 2 Kp square m square plus Ci, I am just drawing it here because we have the graph here. So, plus Ci into Kt Rp divided by Kp square f Kd mq. Of course, from this graph you already found also the value of Kt by Kp square from the slope of the initial linear plot, that you have to keep in mind. So, you know this value of Kp square by Kt. Now, if you are plotting this versus Rp, that also gives you a linear plot. This term, this full term, this is y versus Rp. If you are plotting that, that gives you a linear term, linear plot. The slope of that linear plot will give you the value of Ci. Why? Because Kp square by Kt is already known from the first analysis, Kp square by Kt, and f is known, Kd will be known from different experiments, and m is already known, monomer concentration. So, Ci can be found out from this. Now, when chain transfer to monomer is negligible, which is often the case for many of the systems, then this term will go. I will come to that in a little while. When chain transfer to monomer is negligible, then this term will go. Then you can rearrange this term you bring in here, and what you will get is something like this: 1 divided by xn bar minus, so you are taking this term on this side, Kt Rp divided by 2 Kp square m square equal to Ci into I by m. Now, I am just simplifying this. So, instead of this expression I put back I by m for the simplicity of understanding for you. Now, if you are plotting this versus I by m you know, initiator concentration you know, concentration of m you know. So, if you are plotting these two, this versus this, then the slope directly is going to give you the value of Ci. So, let us say I will show you one experimental graph here. So, on the y axis you are plotting that particular expression, and on the x axis is I by m, and for this kind of system, you know, your this is tert butyl hydroperoxide initiated polymerization of styrene, and the chain transfer constant to styrene is negligible for this, and so you will get a linear plot like this because the Cm is approximately constant. So, you can get the value of Cm and Ci like this. Now, what about this thing? If you go back to the script that I was writing here, what about this? I told you that for many of the systems the chain transfer constant to the monomer is close to 0. So, if you look at some data, it will become evident for you. So, for polymerization of styrene with benzoyl peroxide as the initiator, the chain transfer constant to styrene is 0.00006. Chain transfer constant to the initiator, which is benzoyl peroxide, it is 0.055. So, this is appreciable. So, the initiator participates in chain transfer, that is appreciable, but the monomer, so the growing chain that transfers a growing radical to the styrene and becomes a dead polymer, the process of chain transfer to the monomer, that effect, that particular process does not take place at all, because the Cm, the rate, the chain transfer constant for styrene is very low. So, the limiting the molecular weight of the growing radical by participation of the monomer in the chain transfer process is almost negligible. Now, why this kind of thing happens? Let us say you have a growing polymer chain and you have the monomer in a generic way. Let us draw the monomer like this. So, this is your monomer, right. Now, if you are drawing your monomer like this, how can you do a chain transfer? This proton will be transferred here, it will be, so this will be the dead polymer, this will be the dead polymer. So, this growing chain has been stopped, the radical will now be transferred here and ultimately you will have something like this CH2 CY dot. Now, this bond you have to break for this particular chain transfer process to occur. Now, this vinyl bond is generally very stable bond. So, it is difficult to break, you need lot of energy. So, that is why this process is in general not much favorable, and that is the reason why for many of these systems the chain transfer constant to the monomer is very low, including styrene. Okay. But what about chain transfer to polymer? There can be a chain transfer to polymer also. You can have chain transfer to, I did not talk about solvent, you can actually go into that in the same way. I will talk about the chain transfer agent after. So, you can have the same treatment after. So, these different compounds that can limit the molecular weight of the growing polymer chain, they could be, as I told you, they could be solvent, they could be the monomer, or they could be the initiator, or they could be some added agent in order to limit the molecular weight purposely. Now, what about polymer? Because you may have some dead polymer also, polymer which does not have any radical in it, that is a final polymer chain. That polymer chain can also act as a chain transfer agent. In fact, I should not use this term chain transfer agent, as I told you before that this term is specifically reserved for compounds that you add externally in order to purposely control the molecular weight. So, let us not use this term chain transfer agent in this particular way. So, the polymer also can participate in chain transfer, and it can also have a chain transfer constant to polymer. So, it can do a chain transfer like this, say Mn dot, and you have a polymer that you have produced here. So, you have a chain, long chain, in between you have Y H, this proton can be transferred here. So, that this growing polymer chain is stopped and now a new radical is produced here Y and a dot. Now, this dot can actually grow another polymer chain after, and you can lead to branching of the polymer. So, why do not we introduce this particular term into the expression of Mayo equation? The explanation is very simple. As I told you, the data that are obtained for analysis of Mayo equation are actually obtained at low conversion. So, at a low conversion, that stage the concentration of polymer is so small as far as the chain transfer reaction is concerned that you can actually neglect this effect of chain transfer to polymer. So, this polymer chain transfer, that particular part you can neglect in the equation, that is why we do not talk about the chain transfer to polymer. So, finally, how can you determine the value of Cs? You know, if you go back to that particular expression, the general expression of 1 divided by xn, so you have this term plus Cm, this plus this. We have talked about how to determine the value of Cm and Ci in great detail. We have neglected Cs by telling, number 1, there is no chain transfer to solvent, I mean from there this term could originate of course, and number 2, we have not added any chain transfer agent. Now, let us say we are not adding any chain transfer, let us say there is no chain transfer to solvent, we are adding a chain transfer agent, then this term will tell you the contribution of the chain transfer agent to the chain transfer reaction overall scheme to limit the value of xn bar. So, what about this Cs? That is important because you can purposely add a chain transfer agent sometime in order to limit this molecular weight. So, then you have to know for this particular system what is the chain transfer constant for the chain transfer agent, because the efficiency of the chain transfer agent is very important. So, if you are looking at that particular thing here, so Cs value, you want to find out the value of Cs. So, determination of Cs, let us draw the, let us write down the equation here again. So, it will be Kt Rp, again I am putting the expressions of Rp here. So, Kt Rp divided by 2 Kp square into m square plus Cm plus Cs into S by m plus Ci into I by m. Now, as I told you, the chain transfer agent could be a solvent, I mean the chain transfer could be occurring to a solvent or an added chain transfer agent, which is also called a molecular weight modifier or a regulator, molecular weight regulator. I mean all of these regulate molecular weight, even the initiator regulates molecular weight, but here you are adding something from the outside separately. So, overall as long as you understand the concept, these are the different just the different terminologies, that does not change the overall principle. So, what you can do, first thing you can do is that you can say your Cm is very low, it is possible, generally your chain transfer constant to the monomer is low for many of the substrates. So, if this can be 0, now this could be also 0 if you are taking a very low concentration of the initiator, regardless of whether initiator participates in a big way in the chain transfer or not. Suppose Ci is quite high, then the initiator participation in chain transfer is not negligible, but this term becomes negligible if you start with a very low concentration of the initiator, to simplify matters anyway. So, then what can happen is that you can just have this and this term, and from there you can what you can do is that you just take this thing on this side. So, it will be minus Kt Rp divided by 2 Kp square into m square equals to Cs into S by m, and then you plot this term, this is y equals to mx, you plot this versus S by m. So, you can plot this term versus this term. So, that you can do, and if you are doing that, the slope will give you directly the value of Cs, because these things are measurable, and also for example Rp you can find out, Kp square by Kt you can find out by different means. We have already talked about it when we are trying to determine the value of Cm, monomer chain transfer constant, we could find this value Kp square by Kt, so on and so forth. So, you can do like this. In general, what you could also write is something like this: 1 divided by xn bar equals to 1 divided by xn bar 0 plus Cs into S by m. That means all these terms will come here except this term. So, overall the thing is, in absence of a chain transfer agent, this is the degree of polymerization. So, this is xn bar, let us say 1 by dp, dp is your degree of polymerization, is equals to 1 divided by dp 0. So, dp 0 is the degree of polymerization in absence of chain transfer agent. So, that term comes here, this is in presence of chain transfer agent. Now, degree of polymerization you can find out, S is the concentration of the chain transfer agent that you can regulate, n you know. So, you just plot that, dp 0 also you know, in absence of the chain transfer agent. So, it is easy for you to find out the value of Cs. Or what you could do is, you could plot something like this. There are different ways to measure the Cs. Let me draw the equation and then I will explain this. So, what is this? This is the rate of disappearance of the chain transfer agent. This is the rate of disappearance of the chain transfer agent, and if you look at this particular thing here, the chain transfer reaction, So, K transfer, so chain transfer reaction. So, the rate of disappearance of X A is nothing but K transfer into S into m dot. So, K transfer into S into m dot, and the rate of disappearance of the monomer is nothing but R P, which is equals to K P into m dot. The m dot gets cancelled. So, this ratio is nothing but the ratio of the rates of disappearance of the chain transfer agent to the rate of the disappearance of the monomer. Both of them are experimentally determinable. This ratio you can plot against the ratio of the concentration of the chain transfer agent to the concentration of the monomer, and you can find out the value of Cs. So, we will finish this particular class by discussing finally the utility of this Mayo equation. So, as I told you before several times that this gives you a quantitative effect of the chain transfer reaction to different species. That species could be solvent, that species could be initiator, that species could be monomer, that species could be an added chain transfer agent. For example, if there is a chain transfer to both the solvent as well as an added chain transfer agent, then an extra term might come. And in order to make it more simplified, then probably you are going to use a solvent where there is no chain transfer to the solvent, so on and so forth. So, this is a quantitative effect. And what is the utility then? You can adjust the reaction parameters Kt, Kp, Rp, all these things you can adjust in order to get a desired value of Xn bar. As I told you, Xn bar directly relates to molecular weight, and desired molecular weight is very important. You do not want to go to very high molecular weight, because you know, as for example certain properties may become not good for processability, say viscosity becomes so high you cannot process. You do not want too low molecular weight, because if it is too low, properties like mechanical properties, mechanical strength, they do not develop very well. So, you want a target molecular weight and correspondingly the value of Xn bar. So, suppose your molecular weight is lower than what you want in the particular polymerization, then from this equation what you can do is that you can try to find out what is the value of Ci. So, you have a undesired chain transfer reaction occurring, that is limiting the molecular weight. So, you have to stop that. Suppose the Ci is very high, then what you will do? That means the initiator that you are using is not good in this case, because the initiator is participating in chain transfer a lot and it is limiting the Xn bar. So, then you can choose your initiator accordingly, and suppose there is a chain transfer to solvent also, you can find out maybe. So, that is also limiting, then you change your solvent, you change your initiator, you reduce this value of Cs, you reduce the value of Ci, and you get a higher value of Xn bar, because they are reciprocally related. Let us say, what about say you are getting low value of Xn bar, that means low value of molecular weight. What about chain transfer to monomer? You cannot do much about this, you cannot change the monomer, because you want a polymer of a particular structure starting from a particular monomer. So, if your Cm value is high, that is the limiting factor for your molecular weight, you cannot do much about it. So, chain transfer to the monomer is a limiting factor for the molecular weight control. You cannot do much about it, because you do not change the monomer, but you can do something about it, Let us say you consider the case where you have higher molecular weight than you desire. As I told you, that is also not a desirable thing. So, what you want to do? Then what you can do is you add a chain transfer agent to your system, because chain transfer agent actually limits your molecular weight. But of course, you do not want to add a chain transfer agent which has a higher Cs, or you do not want to go to a particular concentration where there is a lot of chain transfer and your Xn bar becomes low, because even if you want to make it lower, you want it to be in a particular range. So, the measuring the value of Cs becomes important. So, you have to adjust the concentration of the chain transfer agent, you have to choose the particular chain transfer agent, because that chain transfer agent monomer pair, for that particular pair this Cs is valid, because for a particular monomer you have a specific kind of propagating species. For that, when you are adding the initiator, the Cs you can determine, that is for that initiator monomer pair. So, you have to choose then, in this case not initiator, the chain transfer agent. So, that will be for a specific chain transfer agent to the monomer pair, that Cs will be valid. So, you have to, for that particular polymerization reaction, you have to choose the proper chain transfer agent which will give you your adjusted CS value, and then you adjust the concentration of your S, that is the concentration of your chain transfer agent that you are adding, and correspondingly you can find out the value of xn bar. I mean correspondingly you can limit the value of xn bar. So, for example, if you are polymerizing styrene, what is the utility? If you are polymerizing styrene polymer, polystyrene, it is a brittle material, it is not very solvent resistant. So, you want to modify this particular thing. So, then what you can do is you make a copolymerization, say styrene, butadiene, acrylonitrile. Okay. So, these three can be clubbed together and that will give you a good property, suppose. So, this kind of polymerization when you are doing, you have to also regulate the molecular weight. You can use say dodecane-thiol to regulate the molecular weight for this kind of, for specific kinds of polymerizations. So, that is an important part to tell you that we indeed use say chain transfer agent to limit the molecular weight. So, speaking about in the passing about the properties, so these kind of copolymers are also important. We will talk about that when we talk about in some way, in some detail when you talk about copolymerizations after, since we were talking about styrene butadiene copolymer, it is important to mention this, that styrene is a brittle material, polystyrene, and when you are putting say acrylonitrile to it and when you are putting butadiene to it, it is giving it a elastomeric property, it is giving it a stretchable property, plus it is also giving it a solvent resistant property. So, say for example, this copolymerization reaction, this is an important reaction, then industrially important, and for that also you are using say chain modifier. So, you indeed use this kind of equations for real practical utility situations. So, as far as this particular class is concerned, we will stop now. I guess we have discussed different facets of this Mayo equation, and I hope I have been able to impress upon you the fact that these equations, the quantitative effects are important. The complexity of all these different terms being clubbed into the equation notwithstanding. So, what we will do in the next class is we will talk about auto acceleration phenomenon that is observed in radical polymerization process. Till then, goodbye and thank you.